In this tutorial we're going to have a look at how to convert a complex number from polar form to rectangular form. A polar form looks like the expression on the left hand side here. Z, which is our complex number, is equal to R, which is usually called the modulus of the complex number, times E, theta. Theta is called the argument of the complex number. The rectangular form, which is the one that we want to be able to write our number into, looks like the one on the right hand side here, which is a plus ib. So the same number can be expressed as a plus ib, where a is called the real number of the real part of z, and b is the imaginary part of the complex number z. So in order to be able to solve this type of problems, we need to remember the so-called Euler relation. Euler relation lets us transform e to the I theta, so any exponential expression with an imaginary argument, to a set of trigonometric function, to an expression which has trigonometric functions. And in particular, e to the I theta is going to be always equal to cosine theta plus I sine theta. This is called Euler's relation. And the way to apply this is to be able to recognize in our expression what theta is, and then just write down e to the I theta as cosine plus I sine. Let's have a look at an example. So this is our first example, and in this example we have 2 times e I pi over 3. So let's rewrite here the fact that e I theta is equal to cos theta plus I sine of theta. And we have to identify in our e to the I pi over 3 term what's our theta. Well, if we inspect this expression and this expression, we see that the I is there, and therefore theta must be whatever multiplies the I, which is pi over 3. So in our case, we can simply leave 2 as the modulus for a moment, and then write down within brackets e to the I pi over 3 as cosine theta, which is pi over 3, plus I sine of theta, which is pi over 3. And now it's just a matter of using our calculator or our knowledge of trigonometric functions to express cosine of pi over 3 and sine of pi over 3 as two real numbers. So in this case 2 multiplies the cosine of pi over 3, which is equal to 1/2. And you can check that on your calculator if you're not sure, and plus I sine of pi over 3, which is square root of 3 over 2. And when we multiply that out, we get 2 times 1/2, which is 1, plus 2 divided by 2, which is 1, and we're left with square root of 3i. So the real part of our complex number z is 1, and the imaginary part is pi over 3. A slightly more difficult situation occurs when we have a negative exponent to the e term. So our argument is negative, we could say. Well, in that case, we want to use exactly the same formula, exactly the same Euler's relation, which is e to the I theta equals to cos theta plus I sine theta. But we have to recognize that what's multiplying the I term here, it's not only pi over 4, but also this minus sign. So our theta, in this case, is going to be equal to minus pi over 4. Then we can just do what we've done for the previous example. So we leave square root of 2 as our modulus for a moment, and we rewrite e to the minus pi I pi over 4 as cosine of minus pi over 4 plus I, the sine of minus pi over 4. And at this stage, well, we can again use our calculator to find these two expressions in terms of real numbers. But you will notice that if you remember about sine and cosine's properties, the sine of minus an angle is equal to minus the sine of that angle. So in fact, whenever we have a minus sign in our Euler's relation there, we will have a minus sign in there next to the theta, but that corresponds to having a minus sign in front of the sine term. Okay, so another way to solve these type of problems is to remember the relation for the complex conjugate of Euler's formula, with e to the minus I theta equals the cosine of theta minus I sine of theta. That's only true if there is a minus in front of the I of the exponential. But regardless of whether you want to use that method or not, you could do without it by just plugging the minus pi over 4 inside the brackets there. So my suggestion is actually not to remember that by heart, but to remember the positive version of Euler's relation and using a negative argument when you replace theta. So in this case, what we obtain is square root of 2. Well, we know that the cosine of pi over 4 is square root of 2 over 2. And that's true also for minus pi over 4, as you can check in your calculator. So that's going to be square root of 2 over 2. That's plus I, which remains the same. Well, in this case, we have minus square root 2 over 2. And this simplifies down to square root of 2 times square root of 2 is 2, divided by 2 is 1, plus, actually minus, 1i. So in our case, in this specific exercise, we found that the real part is 1 and the imaginary part is minus 1. Another trick that we can use in order to be able to solve these problems without remembering Euler's formula, actually without even going explicitly through it, is to realize one thing that has to do with Argand's diagram. So we usually draw complex numbers in a diagram which has the imaginary part and the real part as the y and x axis. And we draw them by putting the real parts on the x-axis there. Sorry, that's a in our example earlier on. So if we have a there and b here, which is the imaginary part, we can draw the complex number like that, and our z, which is this number here, can be represented as an arrow that goes from the origin to the point z, which is a plus ib. The polar expression of this number is r e to the I theta. What that means, though, in terms of this diagram is very simple. It just means that theta is this angle here, and r is the length of the arrow. Knowing that, we can use the properties of right triangles. In this case, our triangle is r, angle theta there, right angle here, and then we have a and b, because this one is essentially the same as b. Well, if we know that, we will know that b is equal to r times the sine of theta, and a is equal to r times the cosine of theta. So we could have found a and b by just doing r sine theta and r cosine theta, and then joining them together, adding them together to find z as a plus ib. So let's apply this two formula that I've just derived to our previous exercises. So if we did this in the first exercise, in the first problem, well, what we would find is that we have to identify r, which is 2, theta is equal to pi over 3. Well, and a, I'm going to write them down here, would be equal to r cosine of theta, but that's equal to 2 cosine of pi over 3, and b is equal to r sine of theta, and that's equal to 2 sine of pi over 3. So a is equal to, well, we know that the cosine there is 1/2 times 2, so that's going to be 1, and b is equal to 2 times square root of 3 over 2, which is square root of 3. So we could have found exactly the result of this exercise by applying those formulas.